A physicist opens a dusty old book in 1968, finds a random equation he doesn't understand, and accidentally unlocks what might be the secret to how the entire universe works. That equation would go on to obsess thousands of the smartest people alive for over 50 years. So what the hell did he find? I'm FactSpark. If you're into ideas that break your brain in the best way possible, subscribe right now. Let's get into it. Picture this. Italy, 1968. A young physicist named Gabriele Veneziano is digging through old mathematical literature when he stumbles onto a formula written by the mathematician Euler, a formula from the 1700s. Veneziano notices something strange. This ancient equation seems to perfectly describe the behavior of particles inside atomic nuclei. He had no idea why it worked. He just knew that it did. That accidental discovery lit a fuse. Within a year, 3 physicists, Yoichiro Nambu, Holger Nielsen, and Leonard Susskind, figured out what Veneziano's formula was actually describing. It wasn't just a quirky mathematical trick. It was the equation of a vibrating string. A very particular kind of string. And the deeper scientists looked into it, the weirder and more powerful it became. Here's the first thing you need to understand about string theory, and this is where it gets genuinely wild. Key 1. What string theory actually is. For decades, physicists had been working with the idea that everything in the universe is made of particles, tiny point-like dots of matter with no size, no extension, nothing. Just points. The electron is a point. The quark is a point. Everything fundamental is a point. String theory says, what if that's wrong? What if, instead of points, the most fundamental things in the universe are tiny, one-dimensional threads, strings, that vibrate? Not metaphorically vibrate, actually vibrate, like the string on a guitar. Now here's what makes this idea so seductive. A guitar string can vibrate in different ways. You press different frets, you get different notes. Do, re, mi, fa, sol. Different frequencies, different sounds. String theory says the fundamental strings of the universe work the same way. Each different mode of vibration produces a different particle. One vibration pattern gives you an electron. A different one gives you a quark. Another gives you a photon. Instead of a zoo of completely different particles with completely different properties, you get one single object, a string, playing different notes. That's the pitch of string theory in a nutshell. One ingredient. Everything else is just music. But wait, if strings are real, why can't we see them? Why do particles still look like points when we smash them together in particle accelerators? Size. The strings would be approximately 100 times bigger than what's called the Planck length. That's 10 to the power of negative 33 meters. Write that out and you get a decimal point followed by 32 zeros and then a 1. They are millions upon millions of times smaller than a single electron. At any scale we can currently probe, a string would be completely indistinguishable from a point. We'd never know the difference with our current instruments. So we can't see them. Fine. But does replacing points with strings actually solve anything? Or is it just a more complicated way of describing the same thing? It solves something enormous. And this is where string theory stops being just a cute idea and starts looking like something genuinely revolutionary. Key 2. Gravity shows up uninvited, and that changes everything. In 1974, Joel Shirk and John Schwartz were studying the strings in this theory and found something nobody was looking for. Among the possible vibration patterns of a closed string, a string looped back on itself like a tiny rubber band, there was a state with no mass and a spin of exactly 2. If you know anything about particle physics, that description should ring a bell, because that's the exact description of the graviton, the hypothetical particle that carries the force of gravity. Think about what that means. For decades, one of the biggest unsolved problems in all of physics had been how to reconcile quantum mechanics, which governs the very small, with general relativity, which governs gravity and the very large. Every attempt to build a quantum theory of gravity had exploded into mathematical nonsense, producing infinite results that made no physical sense. And here, without anyone asking for it, gravity just appeared. Spontaneously.
as a natural consequence of the mathematics of vibrating strings. And it gets better. Not only does the graviton appear, but the full equations of Einstein's general relativity, the equations that describe how mass curves space and time, can be derived from string theory. They don't need to be put in by hand. They fall out of the theory on their own. The people working on this at the time could barely believe what they were seeing. A theory that started as an attempt to describe nuclear physics was quietly producing a quantum theory of gravity as a side effect.
Now, I want to pause here and ask you something. And I genuinely want to know your answer in the comments. If string theory turned out to be correct, which part of it would blow your mind the most? The idea that particles are actually vibrating strings? Or the idea that gravity is just one note in a cosmic symphony? Tell me below. I read everything. Key 3. Supersymmetry. The universe has a secret twin. When physicists started working seriously with string theory, they discovered something. For the mathematics to be consistent, for the theory to actually work without producing nonsense, a very particular kind of symmetry had to be built into the theory. This symmetry is called supersymmetry, and it's one of the boldest ideas in modern physics. Here's the basic concept. In quantum physics, every particle falls into one of two categories. There are fermions, particles of matter, like electrons and quarks, and there are bosons, particles that carry forces, like photons, which carry light, and gluons, which carry the strong nuclear force. These two categories seem completely separate. They have different properties, they behave differently, they obey different rules. Supersymmetry says, what if every fermion has a hidden partner, a boson, with the same mass but different spin? And every boson has a hidden partner that's a fermion? The electron would have a partner called the selectron. The photon would have a partner called the photino. For every particle we know, there would be a superpartner we haven't found yet. Now, why would anyone believe this? Because supersymmetry solves real problems. It helps explain why the mass of the Higgs boson, the particle discovered at CERN in 2012, doesn't spiral out of control mathematically. It potentially unifies all the forces of nature at extremely high energies. And it offers a strong candidate for dark matter, the mysterious stuff that makes up roughly 85% of the matter in the universe, but that we've never directly detected. The reason supersymmetry matters so much for string theory specifically is that without it, the theory breaks down. Supersymmetry isn't optional. It's required for the mathematics of strings to be consistent. This is why the full theory is often called superstring theory, rather than just string theory. Key 4. The universe has 10 dimensions, and we can only see 4 of them. This is the part where people either lean in or walk away, because the mathematics of superstring theory, when you work through it fully, produces an unavoidable result. The strings don't vibrate in 4 dimensions. They vibrate in 10. We experience 4 dimensions, 3 of space, up, down, left, right, forward, backward, and 1 of time. But the equations of string theory require 6 additional dimensions of space that we somehow don't perceive. Where are they? The most widely accepted answer was proposed by physicist Oscar Klein, building on earlier work by Theodore Kaluza, and it goes like this. Imagine looking at a garden hose from far away. From a distance, it looks like a one-dimensional line, just a length. But if you zoom in, you realize the hose has a second dimension, its circular cross-section. An ant walking on the hose can travel around that circle as well as along the length. From far away, that circular dimension is invisible. The extra dimensions in string theory work the same way. They're rolled up, compactified in the technical language, into shapes so fantastically small that we can't perceive them, and neither can our most powerful particle accelerators. They exist in every point of space around us, right now, impossibly tiny, wrapped into complex geometric shapes. And here's the fascinating part. The shape of these extra dimensions isn't just a geometric detail. It directly affects the properties of the particles and forces we observe. Different shapes would produce different particle masses, different force strengths, a different universe. Key 5. 5 theories become one. Meet M-theory. Now, you might think, okay, this is all a bit wild, but at least there's one version of the theory, right? No.
When physicists worked through the details, they found that there were actually 5 distinct, mathematically consistent versions of superstring theory. 5, each with slightly different rules, different types of strings, different symmetries. For a theory that's supposed to describe everything, having 5 versions is not great. Which one is correct? Which one describes our universe? For a while, this was an embarrassing problem. Then, in 1995, a physicist named Edward Witten stepped onto a stage at a major conference and announced something that changed everything. He showed that the 5 versions of string theory weren't actually 5 separate theories. They were 5 different perspectives on a single underlying theory. The way 5 blind people touching different parts of the same elephant might give you 5 completely different descriptions of the animal. All 5 were connected by deep mathematical relationships called dualities.
And they all appeared to be limiting cases of one master theory, a theory that lives not in 10 dimensions, but in 11. Witten called it M-theory. What does the M stand for? He was deliberately vague. Some say membrane, because the theory features higher dimensional objects called branes, like strings, but with more dimensions. Some say mystery, because the full theory remains unknown. Some say mother, as in the mother of all theories. Nobody has settled on an answer, because the full theory itself hasn't been settled on yet. M-theory exists as a kind of shadow. We know its outline from multiple directions. We know what it looks like in certain limits, certain approximations. But the complete theory, its fundamental principles, its full equations, remains one of the biggest open questions in theoretical physics. Key 6, the landscape, and the terrifying problem of too many solutions. Here's where string theory faces its deepest challenge. And this is important because understanding this challenge is the difference between actually understanding string theory and just thinking you do. In physics, there's a difference between a theory's equations and its solutions. Think of it like a game of chess. The rules of chess, how each piece moves, what counts as checkmate, those are the equations. But the actual games you can play, the possible sequences of moves, the positions that can arise, those are the solutions. The rules constrain things enormously, but they don't specify which exact game gets played. String theory's equations constrain what's possible, but the solutions, the actual universes those equations allow, are not unique. The 6 extra dimensions can be compactified in an enormous number of different ways. The geometries that mathematicians call Calabi-Yau manifolds, the shapes that the extra dimensions can take, number around 10 to the power of 500. That's not 50, not 500. That's a 1 followed by 500 zeros. Each different geometry gives a different universe, with different particles, different forces, different constants of nature. 10 to the power of 500 possible universes. That's what string theorists call the landscape. And here's the problem. We have exactly one universe to observe, ours. So how do we figure out which of these 10 to the 500 possibilities corresponds to the reality we're living in? How do we determine which geometry was selected, and why? Why this one out of an almost incomprehensible number of alternatives? The most unsettling proposed answer is the multiverse. The idea that all of these solutions are actually realized, each in its own separate universe, and that we live in the one that allows for stars, planets, chemistry, biology, and consciousness simply because the others don't. This is called the anthropic principle, and it makes many physicists deeply uncomfortable because it's not really an explanation so much as a shrug. A theory that predicts 10 to the power of 500 possible universes and can't tell you which one you're in is, from a scientific standpoint, a theory that's struggling to make predictions. And a theory that can't make testable predictions has a very serious problem. So where does that leave us? String theory is simultaneously one of the most beautiful and most frustrating ideas in the history of science. It naturally produces gravity. It unifies all particles as different vibrations of a single entity. Its mathematics connects to virtually every other area of fundamental physics in deep and surprising ways. It resolves problems that destroy other theories. For half a century, the smartest people on the planet have devoted their careers to it. And yet, it remains experimentally untested. Its fundamental formulation, M-theory, is incomplete. its landscape problem threatens to make it scientifically unfalsifiable. And not a single superpartner predicted by supersymmetry has ever been detected, despite the most powerful particle accelerator ever built searching for them. As physicist Lee Smolin once put it, we have not proved string theory wrong, but we have not found any evidence that it's right either. Or put another way, as the physicist who helped start this whole journey, Daniel Amati, once said, string theory is a piece of 21st century physics that fell by accident into the 20th century. We're still trying to catch up to it. The story isn't over, not even close. There are still questions about black holes and string theory, about the holographic principle, the mind-bending idea that our universe might be a kind of three-dimensional projection from a two-dimensional surface, and about whether supersymmetric particles will ever show their faces in our experiments. That's what we'll be getting into next time. If this broke your brain in a good way, share it with one person who thinks they understand physics. Watch their face when you explain the landscape. And don't forget, tell me in the comments, what part of string theory hits hardest for you? The strings themselves, the extra dimensions, the 5 theories into one twist, or the terrifying landscape? I'll be reading. See you in the next one.